Okay. So, all right, folks, let's begin. We have 66 people on class on Zoom so far. Welcome to this first lecture on machine learning for signal processing. This is, I think, at this point, the 15th edition of the course. And believe it or not, when we began this course, we were some folks. Can you mute your microphones? Someone has your mic. There's some noises. Can we mute the mic? Who is it? Wonderful. Can we identify who it is? What's going on?
It's room 212, like background from room 212. Everybody else is muted.
I think I just muted it. All right, perfect. So, yeah, when we began this course, we were the first institution in the world to have a course on machine learning for signal processing. It got pretty popular very quickly, and then we have courses of the same.
If you're not interested, this is your classmate. Oh, dang. Let me choose.
Wait, so Doherty Hall, guys, those of you in the classroom, please remember that. I mean, I think you missed the post that today's class was going to be on Zoom. Wait, I have more noises. So if you are attending from this class, you're welcome to. But if you want, yes, and I can see you waving your hands. Actually, this also shows me what the class looks like when you're viewing this lecture over Zoom. All right, so let me begin. Welcome again to MLSP. I'm Bhiksha Raj. I'm the instructor, of course, and several of my TAs are currently on Zoom, so you can't actually see them today. You can maybe see Prakash. Let's see if I can bring him up. And yeah, unable to see the rest of it. So, no, but we should be able to... Guys, can you please mute yourself? Thank you. Right. So maybe we'll see everybody on in the classroom or next week. So this lecture and the next lecture are going to be over Zoom. In the meantime, if you have during the lecture, it's supposed to be interactive. If you have any questions, please post them on chat or ask. We will respond. So let me begin. The title of the course is Machine Learning for Signal Processing. So without further ado, let me just jump into the subject. The focus of the course, as indicated by the title, is the central word signal. Now, when I say signal, how do you understand the word signal? Does anybody want to take a guess or give me a suggestion of how you would describe the word signal? Anyone? What's a signal? Anyone at all? If you want to answer, maybe I can just speak on some of you. So, perfect. So, response from a system with varying time. It's a piece of information communicated electronically, information from sensor, any function of interest. All perfectly reasonable definitions, but a signal is fundamentally just a mechanism for conveying information. That's why we call it a traffic signal. It tells you when to move, when to stop. Or gestures. When you're gesturing people, you're signaling people. You might have seen this.
Sorry, 1 second.
Okay. Semaphores are these in the olden days. The railway systems were actually controlled by these people waving flags, and the gestures that they made indicated whether the train should move or stop. These were called semaphores. These days, semaphores are used in software, and they are basically ways of conveying information from one module to the other, and they're signals. Now, so that's a general notion of a signal. It's a mechanism for conveying information. In electrical engineering, currents and voltages and such like are called signals. Again, they're carrying information about variation in something. From our perspective, we're speaking of digital signals, and digital signals are ordered collections of numbers that convey information. And they may convey information typically from a source to a destination or about a real world phenomenon. Folks, can you mute yourself? So let's look at some examples of signals. Audio, for example, audio on your computer is going to be a sequence of numbers. But then it's not a, who is this? Someone is forgotten to. Can we find out who it is that is unmuted? I can mute you. So anyway, then let me. Okay, so audio is just a sequence of numbers, but it's not a set of numbers. The order in which the numbers occur is important. And so the signal is not merely the sequence of set of numbers, but the order in which they occur. And this ordered sequence of numbers represents a perceivable sound. So that's the signal. It's signaling you about a sound. Images. An image is a signal. It's a rectangular and again, we are going to be focusing on digital signals that exist on computers. And so an image is an instance of a digital signal. It's a rectangular arrangement or matrix of numbers where each number actually represents a pixel. So when you actually visualize the image, each pixel is a visual representation of one of these numbers. And these numbers together represent a visual scene. Once again, the arrangement, not just the numbers by themselves, it's the arrangement of the numbers, which was, what follows what. That is key, which actually carries information. So it's an ordered collection of numbers. In this case, it's two-dimensional. But then here are other kinds of signals, like biosignals, signals about the human body. For instance, MRIs. MRIs are, we'll see more about this shortly, signals that live in a different domain than whatever it is they're trying to convey. Or EEG signals, which convey information about brain activity. ECG conveys information about cardiac activity. We have things like optical, forget what C stands for, T is tomography, ultrasound, echocardiograms, and all of these on the computer are ordered arrangements of numbers, and they carry information about something. And so they're signals. In this case, they carry information about the body, their body readings. But again, financial data, stocks, options, other derivatives, these are sequences of numbers, and they represent market trends. So they are signals about the market. And so anytime we speak of signals, we're really speaking of ordered arrangements of numbers which carry information about something. And indeed, the business of processing signals is about processing these ordered arrangements of numbers. And you may not even have thought of the financial market as a signal, but in fact, there are special issues on signal processing methods in finance. So and have various other kinds of data, all of which are signals like network data, readings of weather, any stochastic time series. In each case, a signal is an ordered arrangement of numbers that represents some real world phenomenon. So our title is Machine Learning for Signal Processing. What is signal processing? Signal processing is the acquisition or analysis or interpretation or manipulation of signals. By acquisition, we are speaking of capturing the signal, sampling, or sensing. When we speak of analysis, we're speaking of decomposition, breaking it down, a signal down into its basic building blocks. Or manipulation, like removing noise from it, or coding it, or generating signals. Interpretation, like trying to make sense of it. Detection, such as in radars or sonars, or pattern matching, as in biometrics, iris recognition, fingerprint recognition, prediction, like financial prediction or speech coding, and so on. Now, although I have listed these under different bullets, in reality, when we actually begin performing signal processing tasks, we'll find that the boundaries between these different categories of operations that I've listed are often fuzzy. So this is just somewhat of a rough categorization of the various kinds of things we can do with signals. So when we speak of signal processing, in a typical signal processing paradigm, there are many stages to the process. The first is capture, where you're speaking of actually reading data of the sensor or recovering signals of some modified or noisy version of the data, enhancing whatever information or whatever readings you got. All of these come under capture. The signal captured signal is typically put through a channel. And so there are signal processing stages within the channel, such as coding, decoding, compression, decompression, or storage. And then whatever goes through the channel may go through yet another block, which recovers the original information from whatever came through the channel. Or you could do additional processes like pattern analysis, such as feature extraction or regression, prediction, classification. So this is somewhat of a rough arrangement of the different kinds of stages that you might have in a signal processing paradigm. And then within each of these blocks, you can have signal processing mechanisms. So it's a slightly fuzzy definition of what a signal is and what signal processing is. But roughly speaking, a signal is a ordered collection of numbers that represent some real-world phenomenon. Signal processing is the process of manipulating these numbers to some real-world end. And there is usually a final objective, such as conveying the signal from point A to point B or making inferences from it. Now, the first part of our title is machine learning. So what is machine learning? Machine learning is the science that deals with the development of algorithms that can learn from data, like learning the structure of data, such as in feature extraction, or learning patterns in data, such as automatic text categorization or market basket analysis, or learning to classify between different kinds of data, looking at an image and deciding if it's a flower or not, you're classifying, or learning to make predictions, like predicting, is it going to rain tomorrow? Will someone like this movie? Now, in all of these are processes where the common aspect in all of these examples is the learning, where you're learning to do something better, or in fact, do it at all from data. There's no God-given mechanism that you're born with. The process is learned or improved from data. So machine learning is the science that deals with the algorithms that learn from data. And so when we speak of machine learning for signal processing, we are going to be applying machine learning techniques to the analysis of signals. And ML techniques can be applied to each component of the signal processing chain. In the signal capture component, signal capture is all about getting data about the real world phenomenon, and machine learning can be applied here. So in sensing, like compressed sensing or dictionary-based representations, we will see what these are during the course, or reducing, eliminating noise from the data, denoising. And so you'd have mechanisms like independent component analysis, filtering, separation. All of these are signal processing mechanisms where the manner in which these operations must be performed can be learned through machine learning. Similarly, in a channel, if you're sending data through a channel, you'll be compressing it, you'll be coding it, you'll be compressing it, and then on the receiving side, you'll be decoding it or decompressing it, and how best to do it can also be learned from data through machine learning. The data If we're going to be performing additional stages, processes of the data, then there's the aspect of feature extraction. Where you're trying to extract useful or the most relevant aspects of the data. So here again, machine learning can be used for things such as dimensionality reduction with linear models or nonlinear models. And then again, in modeling and regression, machine learning can be used for pretty much every aspect of modeling and regression, for classification, modeling, interpretation, prediction, you name it. And so what we find is that signal processing, the process of analyzing signals, can be organized into a sequence of discretizable modules and stages, and machine learning can be used in every one of these. And so when we're speaking of MLSP, we are going to be learning about how to apply ML to these various aspects of signal processing. So before I continue, I'm going to just release my first poll. The poll is on Zoom. Please, can you see the poll, guys?
Yes.
Yes.
Yeah.
All right, I have only 3 responses. On the poll itself. So now you can, it's a Zoom poll. If you're not seeing the poll, my apologies. It's supposed to show for everybody. We'll figure this out in the next class, but all right, let me stop here. So as we just saw, there are 4 blocks that we showed in the signal processing chain, and machine learning can be applied to all 4 blocks. That is our answer, right? And so we have 4 blocks in the complete signal processing chain, and ML techniques can be applied to all 4. So in this course, we are going to be looking at MLSP is the process of applying machine learning techniques to the signal processing chain. But then I can look at it different. If I look at MLSP as a whole, there are 4 aspects to it. One is representation, how best to represent signals for effective downstream or upstream processing. Modeling, how to model the systematic and statistical characteristics of the signal. Classification, how do I assign a class to the data? Prediction, how do we predict new or unseen values or attributes to the data? And we're going to be covering the application of MLSP for all of these aspects. So under representations, we'll be looking at algebraic methods for extracting information from signals, how to derive deterministic representations of signals, how to obtain data-driven characterizations, where we learn how to represent data from the data itself using different criteria. So principal component analysis, independent component analysis, non-negative matrix factorization, factor analysis, linear Gaussian models. We will be seeing all of these. We will all be looking at the intersection of representations and modeling. So we'll look at learning-based approaches to modeling data, how to have dictionary representations or sparse estimations, sparse over complete characterizations of signals or compressed sensing, how to perform regression. Now, at the intersection of representations and modeling, line neural networks. That's what neural networks are really, really good at learning representations and modeling functions. But in this class, not only will we not be covering neural networks, you will get penalized for using neural networks any problem. One of the things that has happened in recent times is that as the entire world switches to neural networks, we are forgetting about the classical ways of doing things. And so this class is strictly, oddly enough, I teach the other course on Introduction to Neural Networks. This is anti-neural networks. you're not allowed to use neural networks in anything. If we find you using neural networks in your homeworks, in your course projects, we're going to give you a 0 for it. You can get a C for meddling with neural networks. This is the anti-neural network class. We'll look at MLSP techniques for modeling signals. So how do we obtain latent variable characterizations like clustering, k-means, the use of expectation maximization algorithm, probabilistic latent component analysis. We'll look at the intersection of modeling and prediction. So how we can model time series, Markov models, and hidden Markov models, and linear and nonlinear dynamical systems such as Kalman filtering, particle filters, and nonlinear dynamical models. We'll look at classification and prediction using classical techniques, binary classification, meta classifiers. And that's a whole lot of topics to be covering in one semester. Had we had a little time, there's a wish list that are always present. I would have liked to talk about privacy in signal processing and extreme value theory and dependence and significance measurements. Of these extreme value theories, perhaps the most interesting is easier. But we do expect that you have a fairly strong background in linear algebra. What are vectors? What are matrices? What are the various operations we can perform on these and what their properties are? That you have a reasonably good grounding of probability. What's a random variable? What are probability distributions? And how you can compute distributions of functions of random variables. And you have some familiarity with machine learning techniques. Basically, the idea of learning, modeling, and classification. Of these, if you're not particularly strong in DSP and ML, maybe you can still pick up this necessary stuff from the class itself, but you better be very strong in, or reasonably comfortable at least, with linear algebra and probability. We'll have some guest lectures. Ideally, I would have liked to have 2, but since the semester is slightly shortened, we may not have a second guest lecture, but we will have at least 1 guest lecture, hopefully with Professor Ashwin Shankaranarayanan from the CE, who typically talks about compressive sensing. This introductory lecture is only meant to introduce the class to you. It's supposed to be very light. We actually begin jumping into our topics in lecture number 2. So the course website is very aptly named mlsp2023.cs.cmu.edu. It's active. The course schedule is on the website, and all information about the course, the lectures, the slides, the homework assignments, everything will be made available through the course website. So go please visit it. Here's how the course is going to be graded. You're going to have weekly quizzes, and weekly quizzes, we will have maybe 14 quizzes of which we'll pick the best 12. So these are going to be worth 24 points. Each quiz will give you... Great. So each quiz comprises 10 multiple choice questions on the topics covered in the week. The quizzes will be opened on Friday night and closed on Sunday night. Then you have 4 homework assignments, and these homeworks are like mini projects. They are assigned during the course, and they're going to be worth 50% of your points. Keep in mind that every one of these homework assignments is very important. Do not imagine that you can slack off on one and catch up on the rest, because the people who performed well in the first assignment will also be doing well in the second one. I say make a point of mentioning this because in the past, we've had instances where due to some reason, we were not able to release homework 4, and I had a student fighting with me in my office that he was getting a D because I hadn't released homework 4. He had intended to catch up on homework 4. Well, if you messed up the first 3, you were not going to catch up on 4. You'll also have a final course project where we will assign the project. And each of you will have to, or we will assign a small set of projects from which you can pick one. You will have to make presentations about your project typically. And the project presentation date is most likely going to be about December 8th or thereabouts. The presentations will be in the format of video presentations, and you will be evaluated on your work by peers. There's 1% point in class participation, where we're going to be evaluating your attendance as measured by responses to in-class polls. We're going to take it easy for this first week while we're getting things sorted out. But yes, from the second week on, we will consider your in-class polls to determine if you've attended lectures or not. If you're from Kigali, then this might be a bad time zone for you, in which case you will be allowed to view Panopto videos of the lecture, and Panopto tells us who viewed the lecture and when, and we'll use that to determine your class attendance. Again, I am the instructor. I'm Professor Diksharaj. Let me turn on the camera yet again so you can see what I look like. I'll turn it off so you don't need to see me wiping my nose. My office is in Hellman Building, Gates Hellman room number 6705. I'm always available for you if you ever want to come in and discuss any issues relating to the course or pretty much anything. You can come in at any time. If I'm there, I will talk to you. My email is diksha@cs.cmu.edu. This is my phone number. And if you're wondering where my room is, if you come along Force, and if you're coming from Oakland towards CMU, you will see the Hillman building to your right. And so if this blue rectangle represents Hillman building, and the little pink squares represent the windows on the Hillman building, then the highlighted window is the window to my office. So you will be able to identify my building from the street. We have 5 TAs for the course: Kwang Yuan, Prakash Yadav, Adnan Yunus, Karan Bhadri, and Soham Deshmukh. I believe all of them are on Zoom right now. These TAs will be helping you through the course. We will have office hours, and they will also be helping you in general. Office hour information will be put up on the course website. So, any questions? Gabriel, no, you don't. Any questions? So, yeah, so Jung Hao, so if you haven't taken a signal and system course, it shouldn't affect you too badly. Just recommend it because some things might be easier for you to understand, but our course is going to be focused primarily on linear algebra. You should be fine. Anything else? No. Okay, give me a second, guys. I'm going to go clear my nose. I'll be back. Remind me not to catch a flu during the semester. So quizzes are going to be held on Canvas. We don't really care what programming language you use, but you'd probably be using Python or MATLAB. That should be sufficient. If you're using NumPy, you should be able to do everything in the course. Anything else? Right, okay. So continuing on, the story so far, again, we've looked at what a signal is. We've looked at some types of signals, what is signal processing, what's machine learning, where does it apply in the signal processing chain. I'm going to continue with some additional concepts. We'll talk more about signals, more on what we do with signals. talk about representation, regression, classification, and prediction, and how. All of this is very light. Again, I remind you that this is the first lecture, and so we go easy on you, right? Now, we are going to look at, in the rest of the lecture, some principles of signal capture, what those numbers mean, and I'm going to try to explain it through examples. I'm specifically focusing on sound and images, where sounds and images are signals where the purpose of signal capture is to exactly recreate a stimulus. These are the kinds of signals we will emphasize a little bit more in this course, primarily because they're easily interpretable. Please mute yourself. But we'll also look a little bit at MRI, where the signal that you capture is actually not telling you something directly. The numbers you capture is not telling you something directly about an underlying process, but it must be manipulated to make inferences about an underlying system or process. And this illustrates capture in a transformed domain, meaning the numbers you get are not directly related to whatever it is you're trying to capture, but must somehow be transformed or manipulated to recover this information. Let's start with audio. What's an audio signal? A typical digital audio signal is just a sequence of numbers. If you plotted it, it's going to look like this. This is the index, and these are the values. It's just a sequence of numbers. Now, what makes the sequence of numbers sound? This sequence of numbers must represent a quantity that enables near perfect recreation of a sound stimulus. Now, so sound is something that we as humans perceive. So when we talk about sound, we're speaking of a perceptual phenomenon, and the manner in which we perceive it is key. And how do we perceive sound? Now, sound is a pressure wave. It has alternate every time you speak, every time you make a noise, you're moving air. In fact, if I just tap this computer, when I tap this computer, the act of tapping this computer, I'm assuming you're hearing the sound, moves little molecules of air, and this motion of these molecules of air, they actually create little alternating, they create a little pressure wave with alternating highs and lows of air pressure that move through the air. And these variations in air pressure are transmitted through the air to your human ear. So also when we speak, we produce pressure waves by producing puff after puff of air. Any sound producing mechanism actually just produces pressure waves. So these pressure waves eventually go into your ear and move your eardrum. So in your ear is a little membrane, the eardrum, and when the pressure waves go into your ear, the high pressures push the eardrum in, the low pressure sucks the eardrum out, and so the eardrum moves. And the sound you hear is you basically sensing the motion of your eardrum. So here's what your ear looks like. Sound is a pressure wave. It goes through your ear, it goes through this canal. There's a little membrane over here, that's your eardrum, your tympanic membrane, and the sound moves the membrane back and forth. And the motion of this membrane is conveyed through a rather complicated combination of tiny little bones called the malleus, incus, and stapes into something called the cochlea, within which you've got fluid. And the cochlea is this little snail-like organ, really small inside your ear. The motion of these bones moves fluid within the snail-like organ, and the motion of the fluid moves little hair cells inside the cochlea. And what you actually sense as sound is the movement of these hair cells. Now, I'm being somewhat imprecise in my description here, because I actually have a little video from Siemens which explains it very nicely. Now you're going to have to tell me if you can hear the sound here. Can you hear this? Let me see.
Our world is
Can you hear that?
Yeah.
full of infinite sounds. But how do we actually perceive them? Sounds are collected by the outer ear, which consists of the auricle and the external auditory canal. The sound is guided through the ear canal to the middle ear. The sound arrives at the eardrum, a flexible circular membrane, which starts to vibrate when sound waves strike it. The sound waves are passed on by the movement of the eardrum to the middle ear. In the middle ear are 3 tiny bones, referred to as the hammer, the anvil, and the stirrup. Collectively, they are known as the acicular chain. These form a bridge from the eardrum to the entrance of the inner ear. Their interaction increases and amplifies the sound vibrations further before these are relayed fully into the inner ear via the oval window. In the inner ear is the cochlea, which is similar in shape to a snail shell. It contains several membranous sections which are filled with watery fluids. When the sound waves vibrate the oval window, the fluid begins to move, thus setting minute hair cells in motion. These hair cells then transform the vibrations into electrical impulses, which are sent via the auditory nerve and onto the brain. What we call noises are actually just sound waves, which are transmitted through the air.
So it's interesting. What we actually think of as perceiving sound is the perception of the motion of these little hair cells inside your ear. And each of these hair cells is a little tuning fork, which responds to a specific frequency in the sound. And so you have a collection of tuning forks in your ear. And what you think of as sensing sound or hearing sound is sensing the movement of these little tuning forks. And here's an interesting phenomenon that these hair cells are very fragile, and over time they begin to break. The hair cells that respond to high frequencies break first, and then as you get older and older, the highest frequency cells remaining in your ear keep getting damaged. And so the frequencies that you can sense actually decrease with age. Now, that's how we perceive sound. Now, if I'm trying to create a sound signal on a computer, we want to capture this perceptual phenomenon. And so we want to capture the pressure wave using a mechanism that's very similar to what the ear does. So here's what we have. Our microphones, which capture sound, also have a little membrane, a diaphragm, much like your eardrum. And the movement of the pressure waves of sound move this diaphragm. And the motion of this diaphragm causes an electrical signal, current or a voltage, to change in proportion to the movement of this diaphragm. And then, so the motion of the diaphragm is converted to continuous variations of an electrical signal. Now, this is continuous, but then you want to convert it to a sequence of numbers. And so what we do is we read the value of this continuous variation of at regular intervals of time and convert that into a sequence of numbers that is stored. So when you get to the computer, all that remains is this sequence of numbers. What distinguishes this sequence of numbers from any other type of random sequence of numbers? How do we know that the numbers stored on the computer actually have anything to do with the recorded sound? The way we'd know it is if we can recreate the sound that generated these numbers. And the way you would recreate the sound is, these are all just numbers, you'd use these numbers to manipulate the level of an electrical signal. Essentially, these are the values of the numbers that you just captured. And you would, by manipulating an electrical signal, you're basically generating an electrical signal that connects these numbers up continuously in this manner. So now we have a continuous electrical signal. This continuous electrical signal is now going to be used to move another diaphragm, the diaphragm in your loudspeaker. And the motion of this diaphragm is going to create pressure waves, which can sense as sound. And your entire process of recording sound can be thought of as perfect if the pressure waves that moved this diaphragm here when the sound was being captured are identical to the pressure waves generated by this diaphragm here in your loudspeaker when they recreate sound. Now, of course, it's never going to be perfect, but that's the general idea. We capture the movement of a diaphragm to are similar, if not identical, to the original pressure waves. Now, to do this again, we had a continuous signal. We were reading some values at regular intervals from the signal. That's this process of sampling. How many such samples do we want to take? How frequently do you want to read the sound, read the signal? How many samples do you want to take in a second? To understand this, it's convenient to think of sound in terms of sinusoids with frequency. Now, why sinusoids with frequency? There are many ways of thinking about any response to a specific frequency. And so it's convenient to think in terms of the units that our perception itself uses to interpret that. Now, mathematically, any sound may be modeled as the sum of many sinusoids with different frequencies. And again, frequency is a physically motivated unit because our hair cells are tuned to, each hair cell is tuned to a specific frequency. And so any sound has many frequency components. Now, when I speak, all of you are familiar with this notion that sound is composed of frequencies. How many frequencies, what range of frequencies do you think I actually generate? Can anybody tell me? What is the range of frequencies that I actually generate? Anyone? 20 to 200, 100 to 22,000 hertz, 20 to 20,000 hertz. I actually generate frequencies all the way to 1,000,000 hertz. There's no limit to the frequencies I generate. Generation is different from sensing. Your ears only have tuning forks that max out at about 20 kilohertz. But the sounds I generate, they actually go way beyond that. So how does your ear respond to sound? Well, let's see if I can play this. Our ears, we can nominally hear frequencies from 20 hertz to 20,000 hertz, but that's only true when you're a newborn baby. As I mentioned, as you grow older, the hair cells in your ear begin to break up. And so by the time you're about 20, maybe you're hearing 16,000 hertz or 18,000 hertz. By the time you're my age, you're beginning to max out at 12 or 14,000 hertz. So how many different tones do you hear? No sound? Okay. So if there were no sound, 4. Well, maybe Zoom is not a great medium for this. If we did this in the classroom, it would be better. But typically when I do this, yes, you're deaf to Zoom sounds. But typically when I do this demo in class, I can hear maybe 6 tones, but most students can hear 8 because you guys are much younger than me. Anyway, so the point is sound has all of these frequencies, right? Now, when I speak of sampling frequency, I'm actually referring to the number of samples I take per second, and this is measured in hertz, and which is how many samples do I take per second. And we need the sample frequency to be at least twice as high as the highest frequency we want to represent. So this is what is called the Nyquist frequency. in our ears, we are able to perceive up to 20,000 hertz. So if you want the computer to store all the frequencies we can hear, so that when you recreate the sound, you're recreating all the frequencies a person can hear, then because we can hear up to 20 kilohertz, we want to take up to 40,000 samples, at least 40,000 samples per second. So where does this 2x ratio come from? It comes from our ability to reconstruct the sound. So for example, if I had this sinusoid here, and if I took measurements with high frequency, then I'm going to get all of these little red dots as my measurement. And so when I'm recreating the sound, I'm just going to connect them up. And if I connect these guys up, I'm going to get back the sinusoid. But if I took only one measurement per cycle, if I connect them up, the reconstructed signal, which is shown by the red line, is going to be nothing like the original signal. Even if I take more than one measurement per cycle, if I take fewer than 2 measurements per cycle, and here's what happens. When I connect the signal, these measurements up, the recreated sound is going to be of a much lower frequency than the original tone itself. So for me to be able to recreate a tone that has the same frequency as the original tone, I need to take at least 2 measurements per cycle, if not more, like the one on top. If I take fewer than 2 measurements per cycle, the recreated sound is going to have a lower frequency than my original tone, as you can see in this figure. And so you can see how that works. In these examples on top, I have a little sinusoid sweeping from 0 hertz to 20 kilohertz. When I sample the sinusoid at 44.1 kilohertz per second, and then I use those numbers and recreate sound, this is what I get. This picture here is what is called a spectrogram. The x-axis is time, the y-axis is frequency, and the color at any time, and the color along any column shows you the energy in different frequencies at that time. And so this sound starts off as a pure tone at 0 hertz and goes up to 20 kilohertz. This one is sampled at 44,100 samples per second. Can you hear that? Could you? Okay, right. So because 44,100 samples per second was more than enough to recreate all the way up to 20 kilohertz, I'm able to regenerate all of it. But then if I sample it at only 22,000 samples per second, the highest frequency that 22,000 samples per second can represent with any fidelity is 11,000 hertz. Any frequencies beyond 11,000 hertz, when they are reconstructed, are going to end up appearing as something less than 11,000 hertz. Because higher frequency, I'm sampling at 22,000 samples per second, which is less than twice the frequency. And so when I reconstruct it, it turns up as something lesser. And so here, when I sample at 22,000 samples per second, the numbers in my computer, when I use them to reconstruct the sound, you actually get a sound which goes up to 11,000 and then begins coming back down because the sampling rate was too low to capture the higher frequencies. If I use sample these at 11,000 samples per second, here's what I get. Right? The highest frequency it can represent is 5,500. Frequencies above that begin folding down, but then you can't go below 0, so then it goes back up and then goes back down. So clearly, any frequencies higher than half the sampling rate end up folding back down and get reconstructed as something entirely wrong. So this is for tones. What about real sounds? That's a bit of music, sampled at 44,000 samples per second, which captures all the relevant frequencies in music. But now if I sample this at 3 kilohertz, what happened is everything above 1500 hertz got reconstructed as something lower than 1500 hertz. And this begins to sound like some poor animal that's being strangled. Now, this is not just sound. This also happens for images. Here is a nice little checkerboard. Now, when you take a picture, you're taking a certain number of pixels per inch, and the image has a certain rate of variation. And the number of pixels per inch has to be more than twice the highest rate of variation for the image for the picture to represent the image with fidelity. And so here in the first image, the pixels per inch are kind of low, and you can see that you can only sort of sense the checkerboard for the lowest portion of the picture, and then after that it gets messed up. In the image to the right, sampling it at a high number of pixels per inch, and the picture retains some fidelity well into past the halfway point. Or here's something else that you might have seen. Typically, this is videos. This is a plane flying. That's a propeller. And here's what the video captures. In the video, it looks as if the propeller is absolutely static. Why is that happening? Or even moving backwards? Why is that happening? Anyone? The frames per second. The rotation is there. The rotation matches the frames per second. So when it looks static, each frame is capturing the blades occurring in the same position. So what is happening over here is exactly the phenomenon you see with the sound, that although these things are moving very fast because your frames are too slow, the recreated video gives you the entirely wrong impression. So what we see here is that when you capture at too low a rate, the recreated signal, those numbers don't represent the actual signal because whatever you recreate from it is wrong. And so while sampling at 22 kilohertz per second represented things with fidelity in this region, out here it messed up. And so we cannot, if I'm limited to sampling at 22,000 samples per second, I can't do anything about the sampling rate. What I can do is to make sure that in the portions of the signal where the sampling rate is insufficient and it can cause the reconstructed perceptual sense to be wrong, we can at least make sure that you don't reconstruct wrongly. And so typically what we will do when we are capturing sound is to perform something called anti-aliasing. Even before you sample it, you put it through a filter which cuts off all frequencies above half the sampling frequency. And so if I had this sweep and if it was sampled at 22,000 samples per second, then the anti-aliasing filter would chop off everything above 11,000 hertz. And then when I recreated sound from the resulting sequence of numbers, I'd only get frequencies up to 11,000. And then out here, I would see no more sound because those things had been filtered out. If I were sampling at 11,000 samples per second, the highest frequency it can represent is 5,500. So my anti-aliasing filter would eliminate everything above 5,500 hertz before you sampled. So this makes sure that you only lose information, but you don't have distortions from the wrongly represented components of the signal coming back and haunting you. Now, so there's this business of sampling rate. There's the other one, which is resolution. Sound is the outcome of a continuous range of variations. The pressure wave can take any value, whereas computers store numbers to finite resolution. If you're using 16-bit numbers to store sound samples, a 16-bit number can store only 65,536 values. A 4-bit number can store only 16 unique values. And so this is low resolution, and low resolution results in loss of information. So here, for example, if you had a sound, which was just this little triangle, and I took a sequence of measurements, and each measurement was now represented using a 3-bit number, then or 8-bit number. An 8-bit number can only store 256 unique values. So these things are going to get quantized, rounded up or down to the nearest of these 256 values that an 8-bit number can store. And so this signal here is going to end up looking like this. You may not be able to see it too clearly, but this thing has jagged edges. If I use 3-bit numbers, I can only store 8 values. So this triangle that you are trying to store is going to end up looking like this step pyramid. With 2-bit quantization, it's going to look like this. With 1-bit representation, where you used only 1 bit to represent each sample, although you may be trying to represent this triangle, what you actually end up storing is this little square. How bad is that? It turns out that from a perceptual point of view, it has some effects, but we are actually fairly robust. So these are recordings of Professor Tom Sullivan from ECE, saying his name. Tom has done a lot of really cool things in his life. But what he's most famous for is this database that he recorded in the early 90s, which is used around the world. And so this is one of the samples from his recording, where the recording is where each sample is stored as a 16-bit number.
SULLIVAN.
And it sounds just fine. But then if I store each bit as a 5-bit number,
SULLIVAN.
it begins to sound crappy. At 4 bits,
SULLIVAN.
only 1 bit to store each number. So every sample is either 1 or 0. This signal on top, when represented using 1-bit quantization, is going to look like this horrible thing down here. But when you play it out,
SULLIVAN.
you can still kind of perceive, it's Tom, right? But what happens is this quantization to lower resolution ends up overlaying a whole lot of noise on top of the original signal. Now, for speech, it's not so bad, but signals like music, where the perceptual quality is key rather than the content, it can really begin to offend. Like this is a bit of music. If I do that with 1 bit per sample, you can still hear the music, but it's not very pleasant. So the lesson over here is that when I'm going to transduce a signal like speech or like sound, then you want to what I mean by transducing it is converting this real-world phenomenon like the sound pressure waves into a sequence of numbers on the computer. This must be done in a meaningful manner. It must be done in a manner which allows us to recreate the original stimulus from the signal. So for this, you must be able to sample it fast enough to capture the highest frequency variations. And you want to store with sufficient resolution so that each stored number has sufficient fidelity to what you're trying to capture. And just as a reference for audio, common sampling rates are 8 kilohertz, 8,000 samples per second, or 16,000 samples per second. This is used for speech. Music, we use 32 or 44.1 kilohertz samples per second. The real professionals want to retain all the information of the music, so they typically sample at 96,000 samples per second. The resolution for the individual samples, again, if you're trying to represent speech, 12 bits is enough. For high fidelity speech, 16 bits is enough. But if you want music, typically we will use 24 bits to store each sample. Let me release my second poll. And let's see. Can you guys see this poll? Oh, shoot. I have a sorry, let me stop this poll, right? I have a mistake in the poll. Okay, here are the 4 choices on the screen. Just look at the screen and which one would you choose of these 4? The last one, right? So the only true test to verify that you have digitally captured a sound perfectly is if it is possible to recreate the original sound signal perfectly from the digitally captured signal. Anything less means that you have lost information. So that's so much for sound. Here's another kind of signal, images. Images are also perceptual. Fundamentally, you see them through the eye. What is the eye? The eye is just a camera. How does the eye work? Here's what the eye looks like. It has a lens which is connected, attached to the rest of the eye through a bunch of muscle fibers. It's protected on the front through a cornea. And at the back out here is a sensor, something called the retina, which senses light falling on it. And there's fluid all over the eye, which protects it. We have this amazing feedback mechanism. When you're trying to look at some object, this is a lens. And the lens causes this an image of whatever you're trying to see to be formed on this retina. And if this thing is out of focus, then these muscles will tighten or loosen to change the shape of this lens until the image is in perfect focus. And then you'll measure it. And all of this happens just like that. You don't have to think about it. But then here's the eye itself. The key component of the eye is this retina that actually senses the eye. And here's what it looks like. It is what I call an example of perfectly bad design. If there were if you'd like to believe that there was someone designing our eye, then looking at the eye should tell us that this person was a very poor designer. Why so? Here's what the retina looks like. It starts off with a bunch of neurons. These are not the light sensors. The light goes past these neurons through all of these connections till they fall on these sensors. And then these sensors sense the light and send the information to the neurons. But then these neurons have to send the information back to the brain. So these neurons fold back and punch a hole through these sensors and send a neural cable through this hole into the brain. So the sensors itself come in 2 types. There are 2 separate systems. One set called the rods, because they look like rods. These are fast, sensitive, but they don't have any color sense. And they predominate at the periphery of the eye. Then you have a second set of sensors called the cones, which are not so sensitive. And they actually capture color. And they predominate near the main portion of the eye called the fovea or the macula. So here again is what the eye looks like. Here's the lens. This is the retina. And out here is where the nerves fold back and punch a hole through the retina to go to the brain. So where they punch a hole, you get this little spot called the blind spot because it's basically just a hole. Any portion of the image falling here is not going to be seen. The rods predominate out here near the periphery of the eye. They give you kind of black and white vision. Now, if you think that you're seeing color at the edges of your or at the periphery of vision, you're not really seeing color, you're imagining it because the peripheral sensing is mostly black and white. Now, the cones are found most densely in this area. There's a little dip here called the fovea that has the highest density of cones. But then there's a small region about it which also has a very high density of cones called the macula. And this is the most important portion of your eye. If this is damaged, which is what happens in older people with macular degeneration, then you can no longer see. This is the human eye. We have 1 fovea. For birds like the eagle, they have 2 fovea, which is why they can see a little earthworm from 3 miles up in the sky. Dogs and cats don't have a single fovea, not just a single dot. Instead, they have an elongated slit. Now, the key component of this are the cones. We sense color. And the cones come in three types. The three types of cones have different sensitivities. The x-axis here shows wavelength. The y-axis shows response. And you get three types of cones. What we call the blue cones have this sensitivity to wavelengths. The green cones have the sensitivity shown by the green curve. And the red cones have the sensitivity shown by the red curve. So when light falls on the eye, what this blue cone senses is the integral of all of the frequency wavelengths that fall under this curve. So the so-called blue light sensors respond not just to blue light, but to an entire range of wavelengths, including wavelengths in the so-called green and red regions. And what you observe is that the blue sensors have a response which is very far separated from the red and green sensors, which are very close to one another. And the exact sensitivity of these different kinds of cells depends on the person. It changes from person to person. And in some people, these red and green sensors have sensitivities that are so similar that you cannot distinguish between them, and these people are colorblind. They cannot distinguish between red and green. So, which is why colorblindness is always red-green colorblindness. It's never red. And traffic lights ideally should be red and blue, not red and green, right? So suppose you beam white light on the eye. What happens? The response, what do you think the relative response of the blue, green, and red cones would be if you had white light? White light has all wavelengths at to equal intensity. What would these responses look like? Anyone? And let me know, right? Same for all, right? That's what it's going to look like. But then, suppose I just had these three wavelengths falling on the eye. This is clearly not white light, right? What do you think the response of these three types of cones is going to be? Anyone? It's going to be this height times this. This is also going to be the same. Why? Because what a blue cone senses is going to be the integral of the product of this curve and the spectrum of the actual light falling on the eye. And it turns out that just this combination of these three wavelengths is going to create exactly the same response as white light, and you would see it as white, although it's clearly not white. In fact, there are many combinations of wavelength that produce the same perception of any given color that you see. So our perception is actually very, very limited. Now, in our eyes, we get three kinds of cones, but there are several types of animals that are actually tetrachromatic, which means they have four types of cones. And there is, to my knowledge, there's at least one human, a woman somewhere in UK, who's also tetrachromatic. And so the way their brain represents color is going to be very different from our eye. So how does a digital camera capture images? You're typically going to have a CCD or a CMOS sensor at the back, which has a grid of sensing elements of three colors. And these sensing elements have some density, like between 200 and 600 pixels per inch. The camera typically includes an anti-aliasing filter to eliminate aliasing in the image because you're sampling the image when you take a picture. And what we do is to use the trichromatic nature of human vision. If I want to represent white light, I should be representing all infinite wavelengths. That's something you cannot represent. Instead, what we will do is to say that I'm going to use some canonical combination of wavelengths to represent white light. So when I see white light, I'm going to store this much of one number, this much of the other number, and this much of the third number. And so the three wavelengths that I choose these are what I'm going to call red, green, and blue. And the three wavelengths that we have chosen are 650 nanometers for red, 510 nanometers for green, and 475 nanometers for blue. So it's not true that the world consists of only three colors. The world consists of an infinity of wavelengths. But even our eye senses the infinity of wavelengths. But when we try to recreate it and store it on a computer, we're going to store it in terms of only three wavelengths, with the idea that if you adjust the heights of these wavelengths just right, you can get the same perception or something similar to what your eye can actually see. Now, your eye is not capturing reality, but it can still capture something like 10 million colors. What your digital camera can represent using this very crude quantization is just going to be a fraction of all of those combinations. And so when you see a computer image is just going to be a rectangular grid of numbers. If you zoom in, eventually each pixel is just going to be a number. And if you see the grayscale black and white image, it's going to be a single number where when you display it, you're assigning the same height to red, green, and blue. Whereas, so from the perspective of what you see versus what the computer sees, you would see an image. The computer is just going to see an arrangement of numbers, a two-dimensional arrangement of numbers. When you have color images, then the computer, your camera is actually capturing three different wavelengths, and the sensitivities of these three wavelengths are designed such that when you display the image, then when you display the image, again, you're going to be displaying it purely using red, blue, and green, with their amplitudes manipulated such that the effect on the eye is the same as having the original color that you were trying to see. So again, if I go back here, I might be trying to recreate this wavelength, which is out here. And I'm going to try to recreate the sensation that I've got from this wavelength using these three entirely different wavelengths. The world is represented using red, blue, and green. But what you represent, but the colors that the wavelengths that you represent may not be red, green, and blue at all, right? So if this is your original image, again, this is crappy, right? Because I'm showing this using RGB, whereas in real life, you're going to have an infinity of wavelengths. Your computer is going to store a red image, a green image, and a blue image to represent this colored image. So let me release the third poll. Can you guys see the third poll? All right, 5 seconds. Stop this. For some reason, 2/3 of you thought, 1/3 of you thought that there are only three combinations of wavelengths that can create the impression of white. There are an infinite combination of wavelengths, all of which can give you the same sensation as white light could give. So when you see white, you may not actually be seeing white. You may be seeing something entirely different, just imagining that it's white. And the number of things that could fool you into believing that they are white is infinite in number. Again, on the computer, those pixels are quantized. They're going to be used, you're not using a continuous valued amplitude. You're going to be using a fixed number of bits for each value. Typically, we use 8 bits, which gives you a dynamic range of 1 to 250. much, much less than what humans can sense. We can easily accept a range of 1 to 100,000. And even if you're using 8 bits, most cameras will only use the first 6 bits and the last 2 bits are not going to be used. So they will tell you it's 24-bit images, but it means that you're using 8 bits per color, but of those 8 bits, you're actually only using 6 bits. And so the number of possibilities you get is going to be 2 raised to 18, which is orders of magnitude lesser than the 100,000 cubed colors, that levels of variation a human being can see. So typically when we process color images, we just work off the grayscale images, decode the image from whatever representation you have to red, green, and blue, and average those. For specific algorithms that deal with color, individual colors may be maintained, right? So we just saw some examples of speech and images. Speech and images are special in that whatever you sense and store is directly related to the original stimulus. So the sequence of numbers that you store to represent speech directly represent the pressure value. And so they're a direct facsimile of the stimulus. Similarly, the pattern of numbers that you store for images are a direct representation of the intensity of 3 different wavelengths of light. So they're a direct facsimile of the stimulus. There are other signals where the digitized signal is not a direct facsimile of the data to be represented. The signal is captured in the transform domain, one such as the MRI, magnetic resonance imaging. So here we attempt to image this interior structure of soft tissue. And the way we do it is by imposing a magnetic field and measuring the resonance of protons, of hydrogen atoms. Now, if you look at a cross-section of the human body, if I look at the x-axis here, you see that there are all kinds of interstitial spaces. And these spaces are of different dimensions, different lengths, right? So if I were to beam a magnetic wave of say a wavelength 3 centimeters in the horizontal direction, all of those spaces which are 3 centimeters in length are going to resonate, the rest of them won't. And I can measure this resonance. And then by measuring this resonance, I can tell you how much of this horizontal section consists of spacings of 3 centimeters. Now, if I do the same thing with a wavelength of a magnetic wave of a wavelength of 6 centimeters, I can measure the resonance and I can tell you how much of these interstitial spaces have a spacing of 6 centimeters. I can do the same thing in the vertical direction, right? And so that's what we do in an MRI. First, we take slice-wise measurements, and then at each slice, we scan through a whole series of wavelengths of magnetic waves along both the x and the y axis, and we measure the resonances. And based on the measured resonances, we know what fraction of that particular slice has spacings of different sizes. And in effect, we're computing a 2-dimensional Fourier transform. And so the collection of numbers that the MRI gives you is basically giving you as a collection of Fourier transform representations of the slice from which the actual image must be reconstructed. And we'll be reconstructing it for various slices and join them up for a full 3D reconstruction. So again, let me try to give you the fourth poll. And can you see this poll? All right, 15 seconds, guys. Let me stop this. What do you think the answer is? right? The key thing is that MRIs are captured in a transform domain and must be decoded, whereas X-rays are captured directly in the image domain. So we've seen three different kinds of signals. Two of them which are facsimiles of the stimulus you're trying to record, one of which was captured in the transform domain. And of course, we can have a whole range of other kinds of signals, and each of them would have their own way of capture. What do we do with these signals? We can learn these signals can be decomposed into combinations of building blocks. We can learn what these signals are composed of. Different kinds of signals. You can think of these in terms of Lego blocks. If I've got Lego versus Meccano, then Lego blocks the kinds of objects that Lego blocks can create are very different from the kind of objects that Meccano blocks can create. So different signals of any category can be composed. Signals can be decomposed into combinations of building blocks, and different signals of any category can be composed as different combinations of these same building blocks. So knowing the composing combination, knowing what the building blocks are, and knowing how they were put together to create the signal informs us about the properties of the signal. But for this, we need to know what the building blocks are. If I'm trying to analyze a Lego object by looking at Meccano building blocks, it's not going to tell me anything about the object itself. So the machine learning challenge over here is to analyze signals and find out what the basic building blocks are, and also how these building blocks were put together to recreate the signal. Mathematically, if S is the signal, B are the building blocks, and W is how they're composed to construct the signal, then I can say S equals F of some function F of B and W. And the machine learning challenge is to see lots of signals and figure out what the building blocks B and the combination parameters W are. So also, we look at modeling the signals. Signals are produced by processes, which are generally partially or fully unknown. And for interpreting or making any additional analyses, we need to know what the process underlying the signal is. This is needed for control, prediction, and analysis. The challenge here is to characterize the process underlying the signal, either through the statistical properties of the signal or through an abstract parametric model. And these are the machine learning challenges here. We can perform classification on signals. Signals may arise from different classes of stimuli or processes. And often we need to identify the underlying process or stimulus. And so the machine learning challenge here is to identify the underlying class of the signal. So you might want to look at this picture and figure out if it represents a wash basin or a face. And that's the problem of classification, right? Prediction. Signals can be analyzed to make predictions about the future of the signal or the underlying process. And so now the machine learning challenge here is how to make the best predictions about the future or about the underlying process. So you might, for instance, look at a sequence of stock values and try to make a prediction about or the stock market and make predictions about what it's going to look like in the future, or try to analyze why it behaved in a particular manner. And this is part of the machine learning challenge as well. There's another aspect in all of this, that of supervision. Learning representations, modeling, all of these are preliminary steps of classification and prediction, and can be performed with or without reference to the actual classification or prediction task. So if the manner in which you learn representations refers to the task, then we call it a supervised mechanism for learning representations. If it does not, then we call it unsupervised, and both explicitly optimized. For example, if I'm trying to look at images and trying to detect if it's a face, then an unsupervised representation just learns to describe images. So it would learn to characterize edges, gradations, and so on. The things that it learns to use to describe the data may not actually relate to the problem that you have of figuring out whether it's a face or something else. In a supervised framework, then you're going to automatically learn ways of describing the data that are relevant to the problem, like characterizing nose-like features or eyebrow-like features or mouth-like features, which can help you determine that this is a tap and not face. It's better suited to detecting the underlying task. I just sort of went over some very simple ideas of what it is we're going to be doing, what's signal processing, what's machine learning. We looked at some notions of signals. What are signals? And the fact that when you're the signal is supposed to represent some underlying phenomenon, and that when we capture the signal, the manner in which we do it must relate to the underlying phenomenon or the collection of numbers you get, are not going to be very useful. And then we've looked at different kinds of things that we can do at a very high level with these numbers. We'll delve a whole lot into this in the coming classes. The primary tools of our trade are going to be linear algebra. We're going to use a lot of linear algebra. We're going to use some calculus, some optimization, and some probability. So before we jump into all of our topics, in the next couple of classes, we are going to review linear algebra. Now, if you think you've really understood linear algebra and you're very familiar with it, you probably haven't. So because we're going to try to look at it from trying to understand what the individual components of these linear algebraic operations really mean. So we're going to look at it from the perspective of trying to manipulate data. So the next two classes are going to be important, next three, where we look at algebra and probability and optimization before we jump into other subjects. So I apologize for today's class, not exactly the peak shape. We're at the end of the lecture. I'll take any questions